Hey everyone, welcome back to Calculus 3. This is going to be lecture 17 of the course. And in this section, we're going to get into kind of a challenging area of Calc 3, of multivariate calculus, and that's going to be directional derivatives and gradients. And so we're going to get into what these things mean, and then we'll begin to use them in the coming sections. Okay, so let's go ahead and jump into it. So we'll call this section 3.6, directional derivatives and gradients. Okay, and so let's first start with a kind of motivating example of what a directional derivative can help us with. So suppose I'm going to kind of try to attempt to do a reasonable little drawing here. So suppose we've got some hill, okay, and we've got the x, y, z coordinate system superimposed on this curve here, okay. And let's suppose, right? So this thing has some kind of, it's three-dimensional, right? So it kind of comes out of the page here a little bit. Let's suppose on this hill there's some point, right, that you're standing on the hill, right, at this point. And what we want to try to determine is the inclination toward the x-axis. So namely the slope of the hill, right, in the direction of the x-axis. Now, let's assume that the hill is represented by a function z equals f of xy. Right, so for each xy pair, you've got a certain height in the z direction. And so given this kind of a setup, we could use the partial derivatives, f of x, f, the partial derivative with respect to x, and f sub y, right? We could use these partial derivatives to find the slopes in the x and y direction. And further, these can be combined to find the slope in any direction. Okay, and that's going to be kind of what we're up to for the first part of this section, right? And so that being kind of the setup, we're going to now take this setup and define a new kind of derivative called a directional derivative. And we're going to kind of get there by way of derivation. Okay. Okay, a directional derivative. Okay, and so let's go ahead and talk this through. Right, it might be a little bit of a ways to get there, but we will get there. And so we're going to start by letting f of xy equals z just as before. And we're going to let this is going to be a surface. Okay, it's going to be a surface. And a particular point, x naught, y naught, is going to be some point in the domain of f. Okay, so namely this is some point in the xy plane, right? Then the direction of the directional derivative is given by some unit vector. Okay, so the direction, that's kind of a key concept here of the directional derivative, of course. The direction of the directional derivative is given by, and this is a unit vector, very important. It's given by a unit vector, and here's how we'll denote it. It's going to be u equals cos theta I plus sine theta j. Okay, and here theta is the angle the vector makes with the positive x-axis. Okay. Okay, so this is what we're going to start with. So we're going to start by defining what do we mean by the direction of the directional derivative, right? And that all starts with this unit vector that provides us with the direction, right? So u equals cos theta I plus sine theta j, and here theta is the angle that u makes with the x-axis. Okay, so just we'll be augmenting this picture regularly, but here's your x-axis, your y-axis, and your z-axis, right? And so you're going to have some angle or some vector u, right? And there's going to be some angle theta that u makes with the x-axis. Okay, and here we say that u is equal to cos theta I plus sine theta j. So that should be straightforward, right? That's just basic trigonometry. The fact that you have this z-axis, don't let that confuse you. It's really just, the usual kind of thing here with this cosine and sine, right? Okay. All right, so that's where we'll start. Now, to find the desired slope, right? So remember, we're trying to identify the slope of this point on this curve, or on this surface. To find the desired, to find the desired slope at this point on the surface, what we're going to do is we're going to reduce the problem to 2 dimensions. Okay. We're going to reduce the problem to 2 dimensions. Okay, and how are we going to do that? Well, what we're going to do is we're going to intersect the surface with a vertical plane. This vertical plane is going to pass through the point of interest and is going to be parallel to our direction vector, right? So let's draw a picture here. Okay, so we've got our z axis, our y-axis, and our x-axis. Okay, right, so we've already drawn the u vector, right? Remember, the u vector lives down here in the xy plane. Okay, now there's some point of interest in the xy plane. Well, there's a point of interest on the surface which has a point in the xy plane, i.e. a point in the domain of f, right? So we'll just label that P. Okay. And remember, there's a surface up here, so I'm just going to kind of sketch in this so you can kind of keep this in mind, right? But in here, you're going to have some kind of a surface. Okay. And what we're going to do is we're going to lower an intersecting surface with the xy plane. So we're going to lower a surface down onto this that's going to intersect this point P and is going to be parallel to u. So you can imagine when that intersects the xy plane, you're going to get a line. Okay, and I'm just going to label that L. Okay, that line we'll call it L, right? Okay, and that line is going to go through P. All right, so my picture's gotten a little sloppy here, but that line is going to drop down and go through P, and it's going to be a surface, right, that's getting dropped down perpendicular to the xy axis and parallel to u, right? And so it's going to create a curve. It's going to form a curve along the surface. Okay, and we'll just label that curve C. Okay, so let's pause. So let's kind of rough out a little bit more about what's going on here. So we've got this point P on the surface that we're interested in, right? And that point P is going to have an xy coordinate. It's going to have an xy point in the xy plane that's part of the domain of the function f, right? And what have we done here? What we've done is we've dropped a surface into this perpendicular to the xy plane, intersecting the point P, parallel to the direction vector u. Okay, and so you can kind of imagine there's a surface here, right? And when you do that, there's going to be a particular curve that's going to be implied along that surface, where the plane, the vertical plane, and the surface intersect, and that surface is what we're calling C. Okay, so let's talk this through. So first thing we did was we identified the direction vector u, right? This is a unit vector, very important. Okay, and we said that u is equal to cos theta I plus sine theta j. Okay. Okay, and this is going to tell us this is the direction we're interested of the slope, right? That we're interested in. So, you know, the slope, obviously the slope can be different things depending on which direction, and this is the direction of interest. Okay. Second thing is we dropped a vertical. So we dropped a vertical intersecting surface through P, point P. Okay, we dropped a vertical intersecting surface through the point P parallel to U. All right, U is the direction vector. Okay. And what happens when we do that? Well, when we do that, this vertical plane intersects the surface and forms the curve C. All right, remember the surface is Z equals f of x, y. Right, so this vertical plane intersects the surface and forms the curve C. Okay. All right. So hopefully, I realize this is a difficult, realize this is a difficult thing to represent visually, right? So, but hopefully you can get the idea, right? So you've got your point of interest P. This is on the surface. Drops down. There's an x, y that corresponds to that in the domain plane here. And what we've done is drop a surface that's parallel to U through P. Right, and that's going to create this curve on the surface. Okay. And so then the idea here is that the slope of the surface, right, so this is kind of item 4 here, the slope of the surface at the point P, right, which we said was x naught, y naught was the xy coordinates of the point. But so the point on the surface would have coordinates x naught, y naught, and then f of x naught, y naught, whatever that happens to be. Right, so the slope of the surface at this point, namely this guy up here, in the direction of u, so the slope of the surface at this point in the direction of u is just going to be the slope of the curve at that point. Okay. Okay, so you can see how this kind of simplifies this kind of this sort of model sort of kind of simplify finding the slope on a surface like this, right? Because now what we're talking about is really just the slope of a curve in space. The curve is C, and we've drawn it so that it's parallel to U, and it cuts through this point P in the domain. So it has all of the requirements that we seek, but it's been reduced to a simpler type of problem, right? Just a problem about a slope of a curve in space. Okay. Okay, so let's talk a little more about some of the details here. So the vertical plane used to form C, right? So remember this slab that we dropped down into the picture here. This slab that we dropped down that's vertical. So the vertical plane used to form C, it intersects the xy plane in this line L that we draw here, right? So this line L, right? So the vertical plane used to form C intersects the xy plane in the line L, right? let's go ahead and make that number 5. And this line L can be represented by a pair of equations, right? And so what we could do is we could say x equals whatever x naught happens to be plus t times cos theta, and y would be y naught plus t sine of theta, right? So that's going to be the set of equations that describe this line. Okay. Okay, so that's what L is. L is going to be this line determined by this set of equations here. Okay, and so what does that mean? Well, what it means is for any value of t, right? For any value of t, the point, and we'll call this q of xy, right? Which is really just these guys, right? The point q of xy lies on the line L. Okay, simple enough. Okay, so no big deal there, no problem there, right? And then let's think about, well, let me switch pages here, right? So just to recap, right? We've got this point P of interest on the surface, and we're interested in the slope of that at that point in a particular direction, which we denoted with u. We drop a vertical onto the xy plane, intersecting P and parallel to u, and that creates this curve in space, which we've denoted C, right? That C is going to imply a line in the plane, which is going to have the equations x equals x naught plus t cos theta, y equals y naught plus t sine theta, right? Which we can call, and we can call the collection of all such points Q, and all of those points are going to lie on this line L. Okay. All right. Then, what can we say? Well, for each point, for each point P and Q, there is a corresponding point on the surface. Okay, so let's draw another picture. And so these are really all the same pictures. It's just each time I have to redraw it because something else becomes more important, right? So this is really kind of the same drawing, but there's certain things I'm going to omit this time. Okay, so again, you've got your x, y, and your z. Okay, now this time what's important here is the point P and another point Q, right? And then this line, of course, which we know where the line comes from. That's the line that's generated by the perpendicular that's dropped onto the xy plane through P and parallel to the directional vector u. And so this guy is going to describe a curve, right, which we talked about already as well. Okay, and so let's just try to create some intuition here about the fact that this is happening in space. Okay, all right, and so this is like our point P, just like before, and now we've added another point Q on here just for reference, right? So for each point P and Q, there's going to be some corresponding point on the surface, right? So if I come up here to the top of the surface, then there's going to be this point on the surface, and I can do the same thing with this guy, bring it up to the surface, and he's up there as well. Okay, so this point here, let's see, I'll draw a little arrow there. That one there we can say is x naught, y naught, f of x naught, y naught. Okay, this is the point above P. Okay, and then you have something similar for this one, basically the same thing. And this one we'll just denote as x, y, f of x, y. Right, and this is the point above Q. Okay, so hopefully this drawing is not too terrible. It looks reasonable to me. Okay, now remember in the background here you've got a vector u, a unit vector u, which this line that intersects PQ is parallel to. Okay. Now the distance, what's the distance between P and Q? Well, we're going to need that. So the distance between P and Q is what? Well, we'll call it T. Okay, and it's going to be x minus x naught squared plus y minus y naught squared. Okay. And if you recall how we defined the line previously, all right, we had x equals x naught plus t cos theta and y equals y naught plus t sine theta. So L is defined as x equals x naught plus t cos theta, y equals y naught plus t sine theta. Right, so that being the case, we can rewrite this guy here as the square root of t cos, well, no, not quite that, t cos theta squared plus t sine theta squared. Okay. Okay, and so we can write the slope of the secant line through these 2 points, right, using this information. We can write the, if you imagine a secant line cutting through those 2 points, right, that's what the derivative is kind of based on, the idea of the secant line, that when the points get closer and closer together. So we're gonna run the same operation here, right? So we've got a secant line that intersects those 2 points. Can we identify the slope of that secant line? Sure. So the slope of the secant line going through P and Q is, well, you can think of it like this: rise over run. All right, and that's going to be f of x y minus f of x naught y naught, and then the run is t. That's the distance between the two in the xy plane. Okay, so the distance here is t. Okay, and that's going to be equal to, let's rewrite this in a little bit more detail. X, y in particular, this is going to be f of x naught plus t cos theta, comma y naught plus t sine theta, minus f of x naught y naught all over t. Okay. Right, and so here we have the slope, and it's basically the points are all reflected in this expression. And so what we can do then is we can let t go to 0. Right, we can let the distance between P and Q, all right, this is t, we can let that distance go to 0, and what we'll find is that in the limit we'll have the slope of our point P. Okay, and so letting t go to 0, we have the following definition. Okay, right. So this will be the definition of the directional derivative. Okay, so let's talk this one through. Definition. Let f, right, and so this will also serve as a summary of what we've talked through here. So let f be a function of 2 variables, x and y, and let u equals cos theta I plus sine theta j be a unit vector. All right. Okay, so you've got a function of x and y, you've got a unit vector u. Okay, so what we can say then is that then the directional derivative of f in the direction of u of f in the direction of u, denoted by right, and so here's some notation. the directional derivative is going to be a capital D with a unit vector subscript, and then the function itself. Okay, so the directional derivative of f in the direction of u denoted by this is, right, and then here's what we just basically talked about. Okay, we write that in there, and then it's xy. And it's just going to be equal to the limit as t goes to 0 of f of x plus t cos theta, y plus t sine theta, okay, minus f of xy divided by t. Okay, so that's the directional derivative of f in the direction of u. Now, of course, this is all provided the limit exists. Okay, provided the limit exists. Okay, so this is the definition, and we kind of walked through in the first 20 minutes or so of this video. We walked through where this definition comes from, right? Tried to illustrate it somewhat. Okay, and so calculating directional derivatives in this way is a lot like, it's similar to finding derivatives from calculus 1 using the limit process, right? It's technically the way it works, and it's what it's based on, but it's not in practice a good working approach, right? So let's say this, a simpler working version could be the following. All right, so here we'll say if f is a differentiable function of x and y, then the directional derivative of f in the direction of the unit vector u equals cos theta I plus sine theta j is, right, and so here's a sort of a simpler way to think about it. It's d, right, same notation, right, but here what we're going to do is we're going to take the partial of x times cos theta plus the partial of y times sine theta. Okay, and that's going to give us the directional derivative, right? So it's the partial of x, it's the partial of f with respect to x times the cosine theta plus the partial of f with respect to y times sine of theta. Okay, and so that's obviously going to be a much simpler proposition. We can easily find partial derivatives, and if we know what u is, obviously we have the cos theta sine theta piece, so it's a product. It's kind of a sum product of those. So let's actually walk through a proof of this, just because I think it can be instructive to see basically how this is derived, where this comes from, and how it relates to the thing that we just talked through. We spent a lot of time on it, and I think a lot of it kind of follows that from that. Okay, so we'll start with a fixed point x naught y naught. So for a fixed point x naught y naught, right? So we're talking, this is like our p on the surface here. Actually, this would be the x and y coordinates in the plane that correspond to this p. Okay, so for a fixed point x naught y naught, let's let x equal x naught plus t cos theta and y equal y naught plus t sine theta. Okay, and so this is going to be the line in the plane that passes through x naught y naught and is obviously in the direction of u. Okay, we're going to let g of t, okay, let g of t equal f of x, y, right? So g is going to be a function of these two guys here, right, which are obviously is a function of t, right? So x naught, y naught, remember our fix is a fixed point, and so t is the variable here. Okay. So f is differentiable, right, by assumption, and so we can apply the chain rule that we just learned in the previous section to this function g, right? So g prime of t, right, is going to be what? Well, we're going to basically differentiate with respect to x, multiply times the derivative of x, right? So it's f sub x, xy, times x prime of t, plus f sub y, xy, times y prime of t. Okay. And now what is x prime of t and y prime of t? Well, x prime of t is the derivative of x with respect to t. And so if we look at x, that's just going to be basically cos theta. And similarly here, this is just going to be sine theta, right? Just if you differentiate y with respect to t, that's what you get, right? And so this is all f sub x, xy times cos theta plus f sub y, xy times sine of theta. Okay, so we can get that really quickly. Okay, now what happens, so our definition involved the limit as t goes to 0. So what happens to these expressions when t is equal to 0? So if t is equal to 0, right, what do we get? Well, if t is equal to 0, then x, which is x naught plus t cos theta would be x naught plus 0 cos theta, so it's just x naught. And y was y naught plus 0 sine theta, so it's y naught plus 0 sine theta. And so it's just y naught, right? So x equals x naught, y equals y naught when t is equal to 0. Okay, and so what does that mean? Well, it means that g prime of 0 is just f sub x, and then it's x naught y naught times cos theta plus f sub y, x naught y naught times sine of theta. Okay. All right, so we've gotten to this point, right? So kind of keep this in mind here. Okay, let me flip pages here. Okay. And what we can say also is, by the definition, of g prime of t, right, i.e., so this would be the previous definition. Let me put that in there, i.e. the previous definition. It is also true, right, so key thing here being also, because we're going to tie these two together. It's also true that g prime of 0 is equal to the limit as t goes to 0 of g of t minus g of 0 over t, right? That's just the definition of this kind of derivative, right? And so that's going to also be equal to the limit as t goes to 0 of, and so what are these things? What's g of t in particular, right? This is going to be f of, let's see, x naught plus t cos theta, comma, y naught plus t sine theta minus f of x naught, y naught over t, right? And so this is the definition of the directional derivative, right? And so that ties this, right? So this guy here ties back to the previous page where we said g prime of 0 was this guy. All right, so that means this guy here is equal to f sub x, x naught, y naught, cos theta plus f sub y, x naught, y naught, sine theta, right? And so that's what we were intending to show, right? Just that this was another way to calculate the directional derivative, i.e. using the partial derivatives and cos theta, sine theta. Okay. All right, so that was hopefully that's helpful, just in kind of seeing that these things are all related. These derivatives are all related, and the directional derivative is kind of just kind of a special case, isn't it? All right, so let's talk through just a little bit more of just a little bit more on directional derivatives. Then we'll get into some examples. Okay, so there are infinitely many directional derivatives. Right, that hopefully that's clear. The direction, namely, being the thing that introduces the variety here. So there are infinitely many directional derivatives to a surface at a given point. Okay, basically one for each direction specified by your u vector. Okay, so one for every direction specified by u, right? And so, I mean, that hopefully that's clear, but let's just take a look, right? So like if I draw the same x, y, z here, right? So if I've got, maybe I've got some point, some xy point in the plane. Right now, I mean, obviously, I could draw lines parallel to any direction vector, right? So if it happened to be parallel to the y-axis, it might look like that. If it was parallel to the x-axis, it might look like that. If it was something in between, it might look like that, right? And so you can see how there's infinitely many directions, right, that you could imagine. And so the same thing is going to be true of any surface, right? So if you've got your point up here, then there's going to be slopes in any direction, right? Right. So depending on what direction your u is in, you're going to be talking about a different directional derivative. Okay. So that being the case, two of these directional derivatives are of interest. Two of these are basically going to boil down to just the partial derivatives. Two of these will be the partial derivatives, right? And so those are the ones we're very familiar with: f sub x and f sub y. Okay, so the first one let's talk about, right? So let's say this is going to be the partial derivative. This is going to be the directional derivative in the direction of the positive x-axis. Okay, so it's the direction of the positive x-axis. And in that case, theta will be 0. Remember, theta is the angle between the direction vector and the positive x-axis. So naturally, this will be 0 in this case, right? And so our u here would be cosine of 0i plus sine of 0j. Okay, and so obviously the sine of 0 is 0, so this will just be equal to the I unit vector. Okay, and so the directional derivative, so then d, and I guess you would write a d sub I of f of xy, right, is going to be equal to, just using that previous theorem, it'll be f sub x cosine of 0 plus f sub y sine of 0, right? And so for the same reasons, this is going to be 0. And so what we're left with is f sub x times cos 0, which is just 1. And so here you can see that the directional derivative is equal to f sub x, right? So the partial derivative with respect to x is really a special case of the directional derivative, right, when the direction is just the positive x-axis. The same thing is true in the y direction. Okay, in the y direction. So this would be in the direction of the positive y-axis. Right, and so in that case, theta would be like a 90-degree angle or better said, pi over 2. Okay, pi over 2 radians. Okay, and so u, again, would be cos pi over 2 I plus sine of pi over 2j. Okay, and then again here, cosine of pi over 2 is 0, right? So you're just left with 1 times j, so this is just the unit j vector, the j vector. Right? And so in this case, you've got d, the derivative in the direction of the j vector of f of xy is again going to be f sub x of cosine of pi over 2 plus f sub y of sine of pi over 2. Right, and so here again, this is 0 and this is 1, so we get f sub y. Right, and so these two are equivalent, right, when the direction of interest is the direction of the positive y-axis. Okay. All right, so we can see here clearly then that the directional derivative in these two cases is equivalent to the partial derivatives. And so we can kind of begin to see how these two ideas are connected. Right. Okay, that's a ton of derivation. Let's do a few examples and see what these things look like in practice. Okay. So let's find the directional derivative. Find the directional derivative of f of xy equals 4 minus x squared minus 1/4 y squared. We're going to find the directional derivative of this function at 1, 2, right? So the point 1, 2 in the xy plane, and in the direction of, right? So you always have to have a direction vector, right? And so in this case, the direction vector will be u equals cos pi over 3i plus sine pi over 3j. Okay. All right, so we're going to find the directional derivative of this vector, or sorry, of this function at this point in this direction. Okay. And so we can just apply the previous theorem we saw where we take basically the partials and combine that with the cos theta sine theta piece. Right, so we'll need the partials here. So f sub x here is equal to the derivative of partial derivative of this with respect to x, and so that's a constant, and we have minus 2x. And f sub y, constant, and just need the derivative of this, and so you get 1/2, so negative 1/2 y. Okay, and so that's f sub x and f sub y. And so we can obviously see that the partial derivatives exist and they're continuous, right? Remember, f has to be differentiable, and so what that means is that the partials exist and are continuous, and so that's true here. So we can apply the previous theorem, and we say that the directional derivative of of f in the direction of u, right, is going to be equal to the partial with respect to x times cos theta plus the partial with respect to y times sine of theta. And so we can kind of plug these things in. So this is negative 2x cos theta plus negative 1/2 y sine theta. Okay, and so that's the directional derivative, right? And then we're interested in the directional derivative at a particular point and in a particular direction, and so we can evaluate this function, right? And so d sub u of f, and now where were we interested? This was at 1, 2, right? And then in the direction of pi over 3, so we'll kind of write it like this to note that we're plugging in a particular theta. Okay, and so you get negative 2 and then times 1 times cos pi over 3, again just plugging everything in here, times negative 1/2 times 2 times sine of pi over 3. Okay, and so this would be equal to -2, and then the cosine here of pi over 3 is 1/2. And then this will be -1, and the sine of pi over 3 is square root of 3 over 2. And so you can combine all of this, and this is basically just -1 up here, and so you get -1 and then minus square root of 3 over 2. Right? Of course, you could approximate that with a decimal number if you like, but this is good too. Okay, so that is the slope in the direction of u, in this case. U is makes angle pi over 3 with the positive x-axis, and so this is the slope of the surface in that direction at the point 1, 2. All right, very good. Okay, so that's an example of kind of how to calculate these things. Okay, now let's take a look at, let's do another example. Okay, let's do another example. Okay, so this one we're going to again find the directional derivative of f of x y equals x squared sine of 2y, okay, at 1 comma pi over 2 in the direction of, and our direction vector here is given, well, a vector is given as v equals 3i minus 4j, right? Now, so you can see that clearly we've notated this differently. We're using a v, and that might be a clue that there's something a little bit awry here, right? So if the direction vector given is not a unit vector, it's important to normalize it before we apply the previous theorem. Remember, the previous theorem demanded that the direction vector be a unit vector, right? And if it's not a unit vector, then you're going to get incorrect results, right? And so first thing we need to do is deal with this vector. You can just look at this and tell this is obviously not a unit vector, right? So can we create a unit vector? Yeah, we can easily do that. We can normalize this vector by dividing it by its norm, right? So this is just this is just 3 comma -4. We need to divide by the norm here, which would be 9 plus 16 square root. So this would be basically the vector 3, -4. We want to scale by 1/5. Right? So we'll say 3/5 I plus -4/5 j. So now we have a unit vector, and that's what we'll denote as u. Okay, so now we have a unit direction vector. What about the partial derivatives? Can we calculate those? Let's start with f sub x. Well, that's the partial derivative of this with respect to x, and so this is all just a constant, and so you would get 2 sine of 2y times x, and so a better way to write that would be 2x sine of 2y. And what about the partial with respect to y? Well, the partial with respect to y, again, there we'll have to think of this as basically a constant out front here, and so here we'll differentiate this just like we normally would, and you would get 2 times x squared, and then instead of sine, it's going to be cosine, right? Because we're differentiating with respect to y here, so this would be cosine of 2y. All right, the 2 out front is the chain rule, right? Okay, so the partial derivatives exist and are continuous, so that means f is differentiable, and we can apply our previous theorem. Right, so here remember our u was equal to cosine of theta, our general u, it looks like this, plus sine of theta j, right? And so what we have instead here when we normalize our vector is we have a 3/5 I plus a -4/5 j, right? And so the cosine theta here is the 3/5, and the sine theta here is the -4/5. Okay, so keeping that in mind, All we have to do is go ahead and set this up and plug everything in. Okay, so we would say the derivative of u of f of xy is equal to, so it's f of x times cos theta plus f sub y times sine of theta. And so plugging these things in, you get 2x sine of 2y, and then times cos theta. We'll come back for those. And then f sub y was 2x squared cos 2y, and then that's times sine of theta. Okay. And so what we can do then is we can evaluate this function here at the previous, using all of the given values, right? So d sub u of f, and we're evaluating that at 1 comma pi over 2. And so that's going to be equal to, let's see, yeah, so it'll be 2 times sine of, and then 2 times pi over 2. Okay, and then the cosine theta, again, we just saw that was 3/5. And then plus, and here it's going to be 2 cosine of 2 times pi over 2. And then the sine of theta is negative 4/5 from the previous page. Okay, so we have that. And we can just go through this and see what shakes out. So the sine, this is going to be 0, and this will be 1, right? So, yep, that'll be 1. All right, so we'll get 2 times 0 times 3/5 plus 2 times 1 times negative 4/5. And it looks to me like we are going to get 8/5. Oh, sorry, this will be negative 1, wouldn't it? Yeah, cosine of pi is negative 1, so that should be negative. So we get positive 8/5. Okay, perfect. All right, so that's that one. Excellent. Okay, I think we'll go ahead and pause the lecture here, and we'll pick it up in a part B, as I think we have about maybe 25-30 minutes left, so we'll break this one into 2 sections. Okay, so we'll see you all in part B of this lecture.